Now, the other thing we're doing in this exercise is we're learning how interpolation works. Interpolation is a completely different ball of wax. In interpolation, we are taking a set of points and we're saying, okay, so we know what the values are at these locations. We know what the pH reading is at these various locations. And there they are. Now, on the basis of those knowns, places that we've actually taken a measurement, what do we think the pH is at, say, this location right here, or this location right here, the places that we don't have data for? And so in interpolation, we are interpolating. We're putting a raster on top of these points, and that raster is a prediction somehow generated from these points of each location in the extent of the raster. Sounds like a mouthful, and it kind of is, but the actual operationalization of this in ARC is incredibly simple. What we're doing is using the geostatistical wizard. Now, there are instructions, just in case, in your case, the geostatistical wizard is not available. But, and if it's not, you go to project and look at the licensing and make sure that under geostatistical wizard, you have a check mark that says yes. If you don't, go to configure licensing options. The instructions for tweaking that are in the lab document. In the geostatistical wizard, what you can see is all sorts of different tools for creating a prediction map. Now, again, that prediction map is just basically a raster that sits on top of these points, and it is a prediction for every cell in the raster based on the information that we have. So we're going from a sample to a prediction that fills an entire grid, a prediction for each cell in that grid. Now, there are all kinds of algorithms by which this works. Two really commonly used ones are inverse distance weighting, and here, in this wizard, in the instructions in the lab, we run through this first, and basically we change nothing. We just click through until we get a prediction and say finish. And when we do, we get a prediction map that looks like this. Now, the way inverse distance weighting works is we are basically building a formula that is saying add together this value. So if I want to measure, let's say, a point down here, I'm saying, what is my prediction for this location? What I'm doing is I'm saying, well, it's 6.5 divided by its distance from that location. And I'm doing that for all of these and adding all of those together. So the farther things are away from this location, the less of an influence their values, their attributes are having for my prediction. So I'm saying basically all of these have some effect, but the ones that are closest have more of an effect. And when I add all those together, so each attribute value divided by some function of its distance. Sometimes it's the distance squared, sometimes it's distance cubed. Sometimes there's a theoretical basis for making that choice, sometimes there's not. Anyway, when I do that function using the parameterization that we blew by just a moment ago, and if you want to see it again, here we go. What I said was inverse distance weighting, and we're saying let's look at a neighborhood. So we're only looking at the 15 nearest neighbors, somewhere between the 10 and 15 nearest neighbors based on a neighborhood with these dimensions. So basically saying for each cell of that raster, draw a circle around it and look at the 10 to 15 neighbors that fall within that circle. And then weight their attributes, dividing them by their distance and add them all together. And that ends up giving us a prediction. Now, we could change that a little bit. And this is basically a measurement of our predictions versus our expectations to see roughly what our error is. So there are ways that we can analyze it, there are ways we can tweak it, but if we stick to the approach taken by the default settings, we get a map that looks like this. It's sort of a wooden map in that it's only showing us predictions. It's basically an algebraic equation that's just weighting all the distances and all of the attribute values. There is no model for error, so there is no confidence interval attached to these predictions. There's no understanding from the data the factor by which we might be wrong. And so it's not terribly useful for analysis, but it's really useful for just a basic description, saying, well, based on what I've got, what do I think might be going on in the neighborhood? Now, the other tool we use for this is kriging, which explicitly does allow us to measure what we don't know. And it does this by simulating a bunch of data. If you take a look at how kriging is set up, you'll notice it's much more complicated. The prediction map may look simpler, but the math behind it is much more robust, and it also ends up giving us a confidence interval. I'm going to skip all of the wirehead stuff. I took an entire semester on kriging once upon a time. I remember some of it. I just remember that it was really hard. Okay, I remember more than that. But at the end of the day in kriging, what you do is you look at each point and how far it is from each other point and how different their two attribute values are. So you're looking to see if differences in attribute values are attributable to distance. And on the basis of that, it generates a sort of model called a variogram of the behavior, or the sphere of influence, let's think of it, of each point. So we're saying if you're within a certain distance of each point, it exerts some influence on you, and if you're farther away, it doesn't. And so what kriging allows you to do is construct a model of the influence of the points. It's a little more complicated than that, but it also allows you to put into the modeling an actual regression equation. So you can say, all right, so we're looking at distance, difference in attribute values in pH, but we could also throw in there difference in attribute values of, say, percent clay, and say, does it also depend on that? So kriging can give us a much more robust, much more nuanced depiction of the underlying relationship. Now, again, we don't tell you to modify any of this, but just want you to notice there's a lot you could modify. And at the end of the day, the kriging map gets generated, and it looks like this, a little bit simpler. It's also got a much smaller range, I think you'll see. So when you look at the range in kriging predictions, they are from 5.2 to 7.5. Inverse distance weighting is the same. But the inverse distance weighting is picking up on much more regionalized distinctions. Whereas if you look at kriging, it's actually flattening out the prediction. So our predictions are, you don't see as many localized islands. Kriging is pretty much driving us closer to the mean with its predictions. So that, in a nutshell, is just two different interpolation types, and I've also explained some of the tools that you're using in the 6 lab.